we have seen that force is a vector. So what we are interested in is what happens to forces F1 and F2 when they act on a body, whether they are added, subtracted, or what is their resulting effect on the body. This is what we are going to see in addition of two vectors. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. For addition of two vectors, we use two methods. First, triangle law, and second, parallelogram law. In triangle law, we add two non-collinear vectors, vector A bar and vector B bar, as follows. First we draw vector A bar, then we keep initial point of vector B bar on the terminal point of vector A bar like this, and we join the initial point of vector A bar and terminal point of vector B bar, and this vector gives us the resultant vector R of A bar and B bar, which is A bar plus B bar. Since after the completion of process we get a triangle, hence this is called triangle law. In parallelogram law, we draw vector A bar and vector B bar as the adjacent sides of a parallelogram, and the diagonal which emerges from the initial point of both A bar and B bar gives us the resultant R bar of A bar and B bar, which is A bar plus B bar. This is called parallelogram law because at the end of the method we get a parallelogram. We observe that parallelogram law is a version of triangle law itself, because if we name the parallelogram as O, A, B, C, then we can indicate side AB as vector B itself. So AB bar is nothing but B bar, and here we find same triangle law of addition of A bar and B bar, giving us resultant R bar, which is A bar plus B bar. So the resultant R bar are one and the same in both these methods, triangle law and parallelogram law. To find the resultant effect of two forces acting on a body, we have to add them. Suppose we have two forces, force F1 5 Newton and force F2 3 Newton. To find their resultant effect or combined effect, we have to add them. Now how they are added? First we have to draw force F1, which is 5 Newton. Then we have to draw force F2 3 Newton by keeping its initial point on the terminal point of F1. Then we have to join the initial point of F1 and the terminal point of F2. And this vector, say AB, will be the combined effect of F1 and F2. Let it be F, and it will be F1 plus F2. Now suppose if we consider negative vector of F2, which will be minus F2 3 Newton, then we can add F1 5 Newton and minus F2 3 Newton like this. First we have to draw F1 as usual, then we have to draw minus F2, keeping in mind the initial point of minus F2 to be kept at the terminal point of F1. So this is minus F2 3 Newton, and for combined effect of F1 and minus F2 we have to join the initial point of F1 and terminal point of minus F2. So this vector, say vector CD, gives us addition of F1 and minus F2. Here if we compare magnitude of vector AB and its direction with magnitude of vector CD and its direction, we find that we get entirely different vectors. Note that F1, F2 and minus F2 are non-collinear vectors. Shall we get the same vectors If they are collinear, let us check. If we have two collinear vectors, vector A bar of 3 units and vector B bar of 5 units, then we can add them algebraically. That means we can write their resultant R bar as A bar plus B bar, that is 3 units plus 5 units, 8 units. Because since they are collinear, we will first draw A bar 3 units long, and after that we will keep the initial point of vector B bar on the terminal point of vector A bar and draw vector B bar of 5 units. Now, as we have seen in triangle law, to find the resultant of A bar and B bar, we have to connect initial point of A bar and terminal point of B bar, and that gives us this vector R bar, which is A bar plus B bar, 3 units plus 5 units, that is 8 units. Therefore, when the vectors are collinear, we can add them algebraically. Now, negative of vector A bar will be minus A bar, which we draw like this with opposite direction. So this is minus A bar 3 units, and if we decide to add this minus A bar with B bar, then we first have to draw minus A bar 3 units long, and after that we have to keep this initial point of B bar on the terminal point of minus A bar and draw B bar 5 units. And as decided, we have to connect the initial point of vector minus A bar to the terminal point of B bar to get R bar, that will be minus 3 plus 5, 2 units towards right in direction of B bar. So if we add minus A bar and B bar algebraically, then also we can get minus 3 plus 5, 2 units long resultant R bar. Multiplication of a vector by a scalar means multiplying a given vector A bar by a number. Here, by scalar we mean a number. For example, suppose we have a vector A bar of length say L, then if we multiply a vector A bar by a scalar 2, then it becomes 2A bar, and the new vector that we got will be twice the length of A bar, direction remaining same. Suppose we have another vector B bar, and if we multiply vector B bar by a scalar half, then it will be half B bar, and the new vector thus obtained will be half length of B bar. When we multiply a vector by a scalar say x, then its magnitude becomes x times as much without change in its direction. Since direction remains the same, we get parallel vectors like we have got here. A bar is parallel to A bar, or this B bar is parallel to this half B bar. So whenever a vector A bar is a non-zero scalar multiple k of another vector B bar, then vector A bar is parallel to vector B bar. So the meaning of multiplication of a vector by a scalar is to get parallel vectors or collinear vectors. So if vector A bar is parallel to vector B bar, then A bar is a scalar multiple k1 of vector B bar, or B bar is another scalar multiple k2 of A bar. So if A bar equals non-zero scalar multiple k times B bar, then A bar minus k B bar will be 0 bar, which we write 1 A bar plus minus k B bar equals 0 bar. So we are able to find scalars x equals this one and y equals this minus k, such that x A bar plus y B bar equals a 0 vector. Now from x A bar plus y B bar equals 0 vector, and both x and y not equal to 0 simultaneously. Then we write y b bar equals minus x a bar, that is b bar equals minus x upon y a bar, which implies b bar and a bar are collinear, because here this minus x upon y is going to be another non-zero scalar. Now in the relation x a bar plus y b bar equals a zero vector, if y is non-zero, then we get y b bar equals minus x a bar, or b bar equals minus x upon y a bar, which makes b bar parallel a bar. Or if x is non-zero, then x a bar will be minus y b bar, or a bar equals minus y upon x a bar. That makes a bar parallel b bar. So therefore a bar and b bar to be non-parallel or non-collinear, we must have x equals 0 and y equals 0. Let us see how to represent displacement vector 30 kilometers, which is 60 degrees north of west. We have the directions east, west, north and south. Displacement vector 30 kilometers 60 degrees north of west means this 30 kilometer vector drawn to scale, which is 60 degrees north of west. Second displacement vector that we have to draw is 60 kilometers, which is 50 degrees south of east. This will be 60 kilometers drawn to the scale, which is 50 degrees south of east. In triangle ABC, if AB is represented by vector A bar, BC by vector B bar and CA by vector C bar, then we have to prove that A bar plus B bar plus C bar equals a zero vector. Now we have A bar plus B bar plus C bar equals AB bar plus BC bar plus CA bar. Now according to triangle law, AB bar plus BC bar is AC bar plus this CA bar. Now from the figure, this AC bar is minus CA bar plus CA bar, which is a zero vector. Hence proved. In regular hexagon A, B, C, D, E, F, if A bar and B bar are the vectors represented by the adjacent sides of this regular hexagon, then we have to find vectors represented by the other sides CD, DE, EF and FA. Since this is a regular hexagon, implies that vector ED bar equals minus vector AB bar, that is minus A bar, because they are parallel vectors with exactly opposite directions. Vector EF bar is equal to minus vector PC bar, that is minus B bar. Now we will join points A and C to get vector AC. According to triangle law, AB bar plus BC bar is AC bar, which will be A bar plus B bar. So here we write AC bar equals A bar plus B bar. Next we join points F and D to draw vector FD bar. Now vector FD bar equals vector AC bar, which is A bar plus B bar, because they are equal vectors with same directions. So we write FD bar as A bar plus B bar. Join AD to draw vector AD bar, which is parallel to B bar, and for a regular hexagon AD bar will be twice BC bar, that is 2B bar. Now by triangle law, AC bar plus CD bar equals AD bar. So CD bar will be AD bar minus AC bar, which is 2B bar minus A bar plus B bar. That gives CD bar equals 2B bar minus B bar, that is B bar minus A bar. So we have CD bar equals B bar minus A bar. In regular hexagon, DC bar is parallel to FA bar. So vector FA bar will be minus CD bar because they have exactly opposite direction, which will be minus B bar minus A bar. So we get FA bar equals A bar minus B bar. We write FA bar equals A bar minus B bar. Next, AB bar is parallel to ED bar. So DE bar will be minus AB bar. So DE bar will be minus A bar. Let us write it here minus A bar. Similarly, BC bar is parallel EF bar. They are equal with opposite directions. So EF bar will be minus BC bar, that is minus B bar. So let us write EF bar equals minus B bar. So we have vectors represented by all the remaining sides. Vector CD bar is B bar minus A bar. Vector DE bar is minus A bar. Vector EF bar is minus B bar. Vector FA bar is A bar minus B bar. If you like this video, please like it, share it, and subscribe to this channel. See you in the next video. Until then, keep watching Number Collage. Thank you.